Here is the counterintuitive truth about aneutronic fusion. Even when you reduce neutrons, you do not remove radiation, or materials damage, or hard system trade-offs. And as of 2026, nobody has demonstrated net electric aneutronic fusion power. Aneutronic fuels, especially proton-boron 11, sound like the clean answer. More of the fusion energy leaves as charged particles, not neutrons. Charged particles, in theory, can be turned into electricity more directly. That is the dream behind a lot of Beyond-Tokamak work. But the fuel advantage is not free. The ignition and burn conditions for advanced fuels are far more demanding than deuterium-tritium in the regimes people understand best. You are pushing harder against the Coulomb barrier while trying to keep the plasma stable. You also have to beat a silent killer in hot plasmas, radiation losses, especially Bremsstrahlung. That is the penalty you pay when energetic electrons radiate as they are deflected by ions. At advanced fuel temperatures, that loss can climb fast enough to drain power before fusion can replenish it. So the real question is not how many fusion reactions happened. The question is, does the whole machine close its power balance after every loss is counted? That full accounting is where many optimistic narratives collapse. A fusion plant is not a plasma in a vacuum. It is magnets or drivers, power supplies, heat rejection, first-wall survival, maintenance schedules, and regulatory obligations. Net power has to be measured at the wall plug, not inside the plasma. Recirculating power, the electricity you must feed back into the device, can quietly eat your output. This is also why tokamaks still matter, even in a conversation about alternatives. Tokamak reactor synthesis is the reference maturity point. Any Beyond-Tokamak concept has to beat tokamaks not just in physics, but in uptime, maintainability, and cost. Alternative architectures are real and diverse, from helical devices and field-reversed configurations to pulsed magnetic systems and inertial targets. They expand the option set. Yet none has shown net electric aneutronic power as of 2026. One concrete sign of progress is not a power plant, but a widening experimental base. In 2025, an aneutronic fusion relevant study was reported in the large helical device context. That matters because it pushes advanced fuel discussion beyond tokamak-only assumptions. Still, it does not settle reactor-scale gain, wall plug efficiency, or component lifetime. Component lifetime deserves more attention than it usually gets. Aneutronic does not mean no activation or no damage. You still face side reactions, impurities, and secondary neutron channels. You still get particle damage, implantation, and erosion. Even charged particles can be brutal to nearby materials depending on their energies and ranges. That is why a second 2025 milestone is quietly important. Monte Carlo evaluations of displacement and ion range values in the structural alloy Ti6L4V were published for aneutronic reaction products. It is a reminder that advanced fuels push you into a different particle spectrum. You cannot hand-wave that away with a label like low neutron. You have to model what hits the wall, how deep it penetrates, and how often you must replace parts. Some researchers have looked for exotic plasma states to ease the ignition problem. Work on aneutronic fusion in degenerate plasma reframed part of the debate. Instead of only asking for hotter conventional plasmas, it asks whether altered plasma conditions could change feasibility. It expands theory space but it does not validate reactor operation. On the inertial side, there are proposals too. A small-scale aneutronic reactor concept was proposed in 2016, and a laser-driven aneutronic target design in 2020. They are useful because they force specificity. They also put the engineering stack in your face: driver efficiency, target fabrication, chamber clearing, repetition rate, and economics. A single success on target physics is not the same as a working power plant. Propulsion is the other magnet for aneutronic ideas. The appeal is obvious: high specific energy, potentially lower shielding mass, and charged particles that can be directed. Concept work goes back decades, but these remain concept studies. The hard closure is at the vehicle level: power density, thermal rejection, reliability, and mass fraction, not just the reactor core. So what should senior decision-makers take from all of this? Treat aneutronic fusion as an evidence-gated option, not a near-term capacity plan. The right diligence questions are mechanical and unfashionable. Show me the full power ledger. Show me recirculating power and duty cycle. Show me conversion efficiency, including any claimed direct charged particle conversion. Show me materials spectra, activation pathways, and realistic replacement intervals. If you fund it, fund what still matters, even if the grand promise fails.